Dear students, today we are going to study about the design of columns. Columns or compression members. We have already studied that for any framed structure, column is responsible for transfer of loads from the superstructure to the foundation. So columns will transfer the load which is borne by the slab, then which gets transferred to the beams. The beams transfer the loads then to the columns, and the columns will transfer the load to the foundation. Okay, so columns play a very important role in the transfer of loads in any structural system. The kind of loads which the columns will be subjected to are generally compressive in nature. So these structural elements which experience compressive loads are called as compression members. So here we first define compression member as a structural element which is mainly subjected to axial compressive force. The axial force is compressive in nature. Okay, and columns are a kind of compression members, so about which we are going to study now. Compression members are broadly of two types: columns or struts and pedestals. And how do we make this distinction? For which you must know the effective length of the column, or for the time being you can take the effective length as the height of the column. So the height of the column, for the time being you can choose it as the effective length of column, which must be greater than 3 times the least lateral dimension of the column. Okay, so if you consider the cross section of a column, so here you can see these two figures show the plan view of the cross section of columns, typically a rectangular shaped column and a circular column. Okay, so from the cross sectional view you can find the least lateral dimension of this rectangular shape. You know the width of the column is the least lateral dimension compared to this dimension. Okay, so this width is the least lateral dimension. For the case of circular columns, the diameter is the same throughout, so there is nothing like least. You just have to take the least lateral dimension as the diameter of the circular column. Okay, so any column in which the least 3 times the least lateral dimension, and if you know the height of the column, and if this height or the effective length of the column is greater than 3 times the least lateral dimension, then you call such structural elements as columns. Okay, columns or struts. On the other hand, we can also define pedestals if it is the other way around, that is, the effective length is less than 3 times the least lateral dimension, or in other words, the height of the member is less than 3 times the least lateral dimension. So from which you can identify that the columns are kind of slender members, unlike pedestals. Pedestals are stocky in nature. Pedestals are stocky. They have the height which is less than 3 times the least lateral dimension. Now in this study we will focus only about columns in this chapter. So we will just study about the recommendations of design from IS 456 only for columns and not for pedestals. Okay, we will restrict our study only to columns. Now columns are typically of the following cross-sectional shapes. They are either square or rectangular or circular in cross section. So for the RCC structures in which the columns are typically of any of these 3 cross sectional shapes, and here in this figure you are seeing this as the plan view of the column. It may be either rectangular or circular in shape, and these are sectional views. As you cut through the column along its height and look from the front, you will see these sectional views. We might have a tied column. Tied columns, as you see in this figure, these are longitudinal bars. Okay, these are longitudinal main bars in the columns. Okay, and you have to use something to tie these bars. Longitudinal bars are then tied, and we call them lateral ties. These are called lateral ties if these are separate elements. Okay, you have a lateral tie here, you have a lateral tie here, but you can tie them in a different way also, using spirals. As you see in this figure, you have single reinforcement spiral which continues for considerable length in the form of a spiral. Okay, so this may also be provided. So the longitudinal bars are tied together either using lateral ties, as in this figure, or using spirals, or these are otherwise known as helical reinforcement. Spirals or helical reinforcements. Okay, so this is exactly what we are going to study in this chapter. So let me move on. What are the possible loads on columns? So as we already discussed, columns are basically compression members. The most important force on the column is the axial compressive force. Axial compressive force means if you have a column like this, the force is applied exactly at the centroid. Okay, here, exactly at the centroid, here or here. Okay, exactly, the force is passing exactly through the centroid of that cross section. Then we call it as axial compressive force. But it is very difficult to see columns subjected to axial compressive forces exclusively. Very difficult, very rare is such situations. Generally, columns will be accompanied by moments along with axial compressive force. Why? So following are the reasons why true axial compressive force is rare. Usually this is accompanied by moment also. Why? So this is attributed to the following reasons. It may be due to eccentric load. As you see in this figure, the load may be acting away from the centroid. So as a result, the column will have a tendency to bend. Okay, as a result of the moment which generates due to eccentric loading. So this is exactly what we call as eccentric loading. If the load is acting away from the centroid, then we call it as eccentric loading. This has high chances to cause bending moment in the column. Okay, so this is one situation. What are the other circumstances? Lateral loading may also be possible, as you see in this figure. Not exactly, like in case of wind loads or earthquake loads, it is more likely that the structure gets subjected to lateral loads, sideways loads. As a result of earthquakes or wind, the columns will also experience a moment. Okay, so that can also result in moment to accompany the axial compressive force. The third reason being the rigid frame action due to the monolithically cast beams or slabs. You see this figure. Generally, you see here a framed structure here. The columns will be tied together by beams. Okay, so these, if you observe, the beams are cast monolithically with columns. So columns and beams will function as a single entity. Okay, so there is no joint or anything in between columns and beams. They will be cast monolithically. So at the joint, at the junction, they will behave as a single entity. As a result, if you apply load on the beam and the beam deforms, beam deflects, the columns will also undergo geometric changes to compensate for this, for the deflection of beams. So this is known as a rigid frame action. So since this behaves like a rigid frame, as you apply loads on the beams, the beams deflect, along with which the columns will also deflect. Okay, so these are the possible loads which can come over the columns. Okay, so it is not just axial compressive force, it will be accompanied by moments also. Now what are the other things to be taken care of? We have discussed about the different types of loads on the columns. As a result of these loads, what are the different ways by which the columns can fail? The column, especially the RCC column, the reinforced concrete column, can fail by two methods. It can fail by two modes. It may fail by crushing or it may fail by buckling. And what kind of failure will occur among these will depend upon its length with respect to its cross-sectional dimension. So it depends upon the height of the column with respect to the cross-sectional dimensions. So as we already said, the height or the effective length and the cross-sectional dimension will decide whether it will fail by crushing or by buckling. Okay, so now let's discuss quickly about the different types of loading. So we know what are the different loads, and now we are going to classify the columns on the basis of the loads which come over such columns. So classification of columns on the basis of type of loading. So columns with axial load or concentric load. So that is exactly what you see in this figure. If the load is acting exactly at the centroid of the cross section, then we call it a truly axial load or concentric load. So as we already discussed, it is a very rare to see such kind of columns, but still you can find columns located at the interior of symmetric buildings, so they might experience true axial load or true concentric loading. Okay, so one more thing to be kept in mind is that even if it is a truly axial load and we can design such columns for these axial loads, the Indian Standard Code says that even such columns should be capable to resist minimum nominal eccentricities in loads. So due to unexpected events, moments might develop in such columns also, unexpected events. Okay, so as a result, the Indian Standard Code recommends that even such axially loaded or concentrically loaded columns should be designed to resist minimum eccentricities in loading also. So what are these minimum eccentricities in loading? We will discuss later. So just bear in mind, axially loaded columns are those in which the load passes exactly through the centroid of the cross section, but yet we must design not just for axial load, we must consider that the load gets the column is capable of resisting even smaller moments caused due to minimum nominal eccentricities. Okay, so that should be taken care, and this is one type of column. The other type is the columns with eccentric load. So we know that if the load is acting away from the cross-sectional centroid, the centroid of the cross section, then we call it eccentric load. Okay, these eccentric load can again be of two types. They can be uniaxial eccentricity in loading, or there can be biaxial eccentricity in loading. So that is exactly what you see in these two figures. Okay, see, this is the cross section of the column, and now you can take two axes, one along this direction, one along the direction perpendicular to the first one. So two axes you can choose. Okay, and if the load is acting away from one axis, if the compressive force is acting away from one axis, or if the eccentricity is with respect to only one axis, then we call it as uniaxial eccentric load. Okay, and this kind of columns are most commonly found in the interior and the exterior columns in buildings subjected to lateral loads. So especially when the buildings are subjected to wind loads or earthquake loads, both the interior as well as the external columns will be subjected to uniaxial eccentricity. So this is very common type of column. Okay, so this is most common type of column. Okay, now coming to the biaxial eccentricity, which means that if the load is acting both away from if the load is acting away from both the axes, we have said there are two axes, and if the load is acting away from both the axes, then we call such loads as biaxially eccentric loads. And these type of columns which experience biaxial eccentric loads will be common, especially at the corners of building. Okay, so those columns which occur at the located at the corners of buildings will be subject to biaxial eccentric loads. Now we are not done with the classification of columns. We have discussed about the classification of columns in based on the type of loading. Now before we go further, it is important that we define a term known as slenderness ratio. Slenderness ratio is a very important term. It is a measure of vulnerability of a column to fail by buckling. Okay, as you see, let's take this as a column. Okay, so this is a column. When subjected to loads, we have said it may fail by crushing or it may fail by buckling. So buckling is the change in the configuration. As you see here, there is a bending of the column. Okay, so this is exactly what we call as buckling. So the failure of column occurs by change in the configuration of the column. Okay, the column, the axis of the column, if you observe, it will keep bending like a beam. Like a vertical beam, it will bend and finally it fails as you keep increasing the load. Crushing is entirely different. Crushing is something which occurs when the load exceeds the maximum strength of the column, strength of the material or strength of concrete as is exceeded. The crushing of concrete will occur and the column fails. So buckling and crushing are the two important modes of failure. So slenderness ratio is very important to be determined because it will decide whether the column will fail by buckling or crushing. Okay, so it is a very important measure which indicates the vulnerability of a column to fail by buckling. Okay, so how do you define slenderness ratio? Slenderness ratio is equal to effective length by least lateral dimension. So it is the ratio of effective length to the least lateral dimension. Effective length is represented by the notation small l suffix e, and least lateral dimension we represent it by the letter capital D. Okay, so it is possible to define effective length as a function of the unsupported length of column, that is small letter l. So effective length LE is equal to K into L, where K is the effective length ratio and L is the unsupported length of the column, or it is the true length of the column. Okay, so L is the actual length of the column or the unsupported length of the column between supports. The distance between lateral supports is exactly. So if these are the two supports between a column like this, then this is the unsupported length of the column. Okay, so that is small l. So if you know the unsupported length, you just have to multiply it with the effective length ratio, okay, to get the effective length. So effective length LE is obtained by multiplying effective length ratio K into unsupported length. So where do you get the effective length ratio K? K can be easily obtained from table 28 of IS 456. You refer to page number 94 of IS 456. There you will observe table 28, in which both theoretical as well as recommended values of effective length are given. Okay, so you have to choose the recommended value of effective length from that table. Okay, so here is shown the values of K into L, or directly this will give the effective length of columns for different support conditions. Okay, so if you observe these 6 types of columns, these are of different support conditions. So here it is fixed at both top and both bottom supports. Here it is hinged at one support while it is fixed at the other support. In this case you will observe they are hinged at both the supports. Okay. Here if you observe, it is fixed at one point, but it is free to translate at the other support. Okay, it is fixed here, but this here it is free to translate. It is not free to rotate. Okay, so it is not free to rotate as in this case. The ends are not hinged; they are free to translate only. Okay, so here it is free to translate as well as rotate. Okay, and here if you observe, it is fixed at one point but it is free at the other point. Okay, so these are the different support conditions, and corresponding values of effective length can be obtained from this table 28. So the values of effective length ratio is 0.65 in case of this column wherein the both supports are fixed, but it is 0.8 here when it is fixed at one point and hinged at the other point. Or if it is free at one end and fixed at the other end, then the value of K is 2. Okay, so likewise you can obtain the value of effective length and least lateral dimension if you know the cross-sectional shape. As in this case, if you know the cross-sectional shape of the column, then you can easily obtain the least lateral dimension. So the ratio of effective length obtained from this table divided by least lateral dimension will give you the slenderness ratio. Okay, now we must understand that you see this figure, the buckling of column can occur by two ways or two modes. So the two modes by which the column can buckle is exactly what is shown in this 3D image. You see, this is the buckled configuration of one column, this is buckled configuration of another column, but are they the same? You see, here if you observe, let's look at this figure. The buckling of the column has occurred with respect to x-axis. Okay, it is with respect to the x-axis that this column has buckled. Okay, it is with respect to the x-axis that the buckling of this column has occurred. But what about this column, the second one? This second column has buckled with respect to the y-axis. Okay, it is with respect to the y that this profile of buckling has occurred. Okay, so this bending has occurred with respect to y-axis. So we say that the first column, this particular column, bends about x-axis, and this particular column bends about y-axis. So these are the two ways any column can bend or buckle about either of the two modes. Okay, and based on which we have to define the axis. And you see, this is a circular column. Here if you consider that this is the x direction and this is the y direction, the buckling of column can occur in any of the direction. If you choose to change x in any other direction, any other arbitrary direction, correspondingly the y direction will also change. So x if you change, y will also change. Okay, but in case of rectangular columns, if you see, you have to define xx one axis in a direction parallel to one of its edges. Okay, you have to define an axis parallel to one of its edges, and the other axis should be perpendicular to it. So automatically the other axis will also be parallel to the other edge. Okay, so here, just as we have defined that buckling of column occurs about x-axis and y-axis, here again, this being a rectangular column, rectangular cross-section shape, this can also buckle about x-axis as well as y-axis. Okay, and it is important that we understand what is more probable to occur, whether buckling about x-axis or buckling about y-axis is more likely to occur. Okay, so for which we have already defined the axis, x-axis and y-axis have been defined. Okay, the axis which is defined about the shortest centroid distance, okay, about the shortest centroidal axis, we call it as major axis. So the shortest axis is known as major axis, and the longest axis we call it as minor axis. So these are the two axes defined for rectangular columns. But you know, for the circular column, the cross section is the diameter is the same in all direction, whether it is for this column or this column, the diameter is the same in all directions. So it is immaterial if we take this as x and this as y. You can take it as this as y or this as x. Anything is possible. Okay, anything can be done, but not in case of rectangular cross-sectional columns, in which the shortest axis is taken as the shortest dimension. The axis along the shortest dimension, we call it as major axis. The axis along the longest dimension, we call it as minor axis. So these are the two axes of bending. Here again, as we discussed in circular columns, the bending can occur about x-axis or y-axis. So we call them as bending axis. Okay, but it is important that we can determine whether buckling can occur about x-axis or y-axis, which is more possible, which is more probable. So for which we need to define slenderness ratio about both the axes. So here we have defined slenderness ratio as the effective length to the least lateral dimension. Here in rectangular cross-sectional columns, we have to define slenderness ratio about both the lateral dimensions, both along the major axis as well as along the minor axis. So you carefully observe here, the major axis we called it as xx and was the shortest axis. Minor axis we chose yy as the minor axis, which is the longest axis. Okay, and the dimension, the lateral dimension perpendicular to x-axis, we call it as dx, and the lateral dimension perpendicular to the minor axis, we call it as dy. So dx, the lateral dimensions dx and dy are again defined along major axis and minor axis respectively. Dx is the distance measured perpendicular to shortest axis, and dy is the distance measured perpendicular to the longest axis, minor axis. Okay, so dx and dy are also defined. So these dx and dy are the lateral dimensions of this rectangular column. Now this is a plan view, and here is given the elevation of the column. Okay, so here you see this is the column elevation. The column extends from this lower floor to the slab or the beam of the upper floor. Okay, now you see this is a junction. This is a junction at which two beams intersect. There is a beam going like this and there is a beam like this. Okay, so two beams intersecting, perpendicular beams intersecting at this point. So what is the actual length or the unsupported length if we consider major axis, bending about major axis? Okay, so we have to define slenderness ratio about both the axis, and that is exactly what we are going to do. So let us consider the column is bending about xx axis. So like here the column is bending like this about xx axis. So here about xx axis the column is bending. If the column is bending about xx axis, what is the unsupported length? So the unsupported length is shown here as Lx. Lx is the distance from the lower floor to the bottom of the beam, the soffit of the beam here. Okay, so this is defined as Lx. Okay, this is defined as Lx. And here you find this is Ly. Okay, about minor axis, if you consider the bending about minor axis, if you are going to measure, Ly is the distance measured like this. Okay, so this is because the lateral support for bending about major axis is the lower floor here and the soffit of the beam here. Okay, so this we chose as Lx, the unsupported length. But if bending is occurring about YY axis, then the entire beam from the soffit of this beam, the entire column from the soffit of this beam will buckle like this. Okay, so Ly is defined for the unsupported length because laterally this column is supported at this point. Okay, so Lx and Ly are somewhat different. It is not the same height. So for rectangular cross-section columns of rectangular cross-section, we have to define slenderness ratio about both major axis as well as minor axis. So that is exactly what is tabulated here. So slenderness ratio is equal to Lex by dx. Lex, the effective length about x-axis, or major axis, which is given as kx into Lx. The effective length ratio about x-axis into effective length ratio about x-axis into unsupported length about x-axis, and same way effective length about y-axis into unsupported length about y-axis. So this will give you the slenderness ratio for major axis as well as minor axis. Slenderness ratios have to be determined separately for major axis and minor axis in case of columns of rectangular cross section. Okay, so slenderness ratios can be determined likewise. So we have determined Lex by dx and Ley by dy, both slenderness ratios about major axis and minor axis respectively. And if we know these, then we can classify the columns. So we will classify columns into short columns and long columns. If both the slenderness ratios Lex by dx and Ley by dy are less than 12, then we call such columns as short columns. And those with slenderness ratios, both the slenderness ratio or any of the slenderness ratio, if at least one of the slenderness ratio exceed 12, then we call it as long column. Okay, so for the column to be short, then both the slenderness ratios have to be less than 12. If at least one of them is greater than 12, then we call it as a long column. And what is the mode by which each of these columns shall fail? The short columns typically fail when the material, in our case it is the concrete, when it reaches the ultimate strength, the column will fail. So at this point the column will fail by crushing of concrete. The concrete crushes and the material will fail. So short columns are those columns in which the column shall fail by crushing of concrete. But in case of long columns, as you see here, the failure occurs by buckling. So you see the buckled profile here. As you keep increasing the load, the buckling of column occurs and the deflection, lateral deflection will keep increasing, and at one point the column fails completely. Okay, so short columns and long columns are those columns, those classification of columns which can be distinguished in terms of their slenderness ratios and also by modes of failure. Now let us quickly discuss the caudal recommendations on columns. So we have already discussed the slenderness ratio of column. For it to be short, it should be less than 12. For it to be long, it should be greater than 12. Okay. Now, what is the maximum unsupported length or maximum slenderness limit set by the Indian Standard Code? The Indian Standard Code says the slenderness ratio, but not in terms of effective length to the least lateral dimension. It is in terms of the unsupported length only, L by D. It is not K into L by D, it is just L by D. So L by D for columns should always be less than or equal to 60. Okay, so this you can find from page number 42 of IS code. So the slenderness ratio, maximum slenderness ratio of column is 60. Now coming to minimum eccentricity, we have already discussed in our previous session about columns with true axial load. We said that it should be designed to resist minimum eccentricities also. So for which minimum eccentricity is defined by IS code, page number 42 if you refer, clause 25.4. So the IS code says all columns shall be designed for minimum eccentricity. All columns must be designed for minimum eccentricity. If the eccentricity of loads, external load, is less than the minimum eccentricity, then it should be provided at least this minimum eccentricity. Okay, you have to find this minimum eccentricity at least. If the external load is applied with an eccentricity greater than the minimum eccentricity, then it is fine. It is not required to determine the minimum eccentricity in such cases. Okay, so minimum eccentricity can be computed based on this particular clause 25.4, which says that the minimum eccentricity should be equal to the unsupported length of column divided by 500, that is L by 500, plus lateral dimension divided by 30. So for a rectangular column we have lateral dimensions different. Okay, so as we already discussed, we have different lateral dimensions, so definitely the lateral dimension will be dx by 30 or dy by 30. Accordingly you can define different minimum eccentricities for different axes. Okay, for both axes you can differently determine the minimum eccentricities, and you will design the column for this minimum eccentricity. Now coming to the longitudinal reinforcement, there are certain recommendations, very important recommendations. Page number 48 you refer about the longitudinal reinforcements. These are longitudinal bars in columns. It is very important that the longitudinal bars have to be provided in RCC columns, and they shall obey certain conditions as recommended by the code. So the code says the cross-sectional area of these longitudinal bars. So the cross-sectional shape you see for the cross-sectional of the cross-section of the column is shown here, both rectangular as well as circular, in which you can see the longitudinal bar cross-sections. Okay, so these longitudinal bars can be seen. So you can actually determine the area of these cross-section of bars, longitudinal bars. Okay, and if you find it, the cross-sectional area of longitudinal bars should not be less than 0.8% of the cross-sectional area of the column, of the gross cross-sectional area of the column. So of the total cross-sectional area of the column, the cross-sectional area occupied by the longitudinal bars should not be less than 0.8%, and it should not exceed 6%. Okay, so the cross-section area of the longitudinal bars should be somewhere in between 0.8% and 6%. Okay, so remember, it is a very important condition to be remembered. Just keep it by heart. Okay, the cross-sectional area of longitudinal bars in the column cross-section should lie between 0.8% and 6%. Okay, so this is useful for the design. Now another important recommendation is that the minimum number of longitudinal bars provided for columns should be 4 in rectangular columns and should be 6 in circular columns. So minimum bars to be provided for rectangular columns is 4, and for circular columns it is 6. And what is the minimum diameter of the bar to be used? For columns it is important that bars of diameter less than 12 should not be used. You must always use bar diameter, longitudinal bars of 12 mm diameter or more. Okay, now coming to the spacing of longitudinal bars, you can provide longitudinal bars any number of bars in between, but it should satisfy these conditions. But the spacing should not exceed 300 mm. So that is the the spacing of longitudinal bars measured along the periphery of the column. So as you measure along the outside of the column, the spacing between the bars, center to center spacing between the bars, should not exceed 300 mm. Okay. Now coming to the cover to be provided for columns, reinforcement should be provided with a cover, clear cover to be provided to ensure its safety and serviceability. So for this purpose, we have already seen this table 16A of IS 456 in page number 47. Therein you will find that the minimum clear cover to be provided for columns is 40 mm. So for columns, the minimum clear cover to be provided is 40 mm. Okay, and that too, the clear cover has to be provided not outside the longitudinal bars. It should be outside the links, it should be outside the ties which we provide. So here you see we have provided longitudinal reinforcement, and on outside of it you are providing ties or spirals. Okay, so outside these ties or spirals, in addition to the side to the outside of spirals or ties, you have to provide this clear cover. 40 mm minimum should be provided. Now coming to the transverse reinforcements. So transverse reinforcement is what we have seen as lateral ties or spirals. So we call it the actual terminology to refer to the lateral ties or spirals used in columns is known as transverse reinforcement. So we must call them as transverse reinforcements. And why do we have to provide transverse reinforcements? Transverse reinforcements are play a very important role in the functioning of columns. They are provided to confine the concrete. So you know the concrete is very strong in compression but weak in tension. So if you provide confinement to the concrete, it will further increase its strength, compressive strength. Okay, so by confining concrete, the transverse reinforcement helps improve the strength of concrete. Okay, so transverse reinforcements also is helpful to hold the longitudinal bars in position. They are held in correct position. The longitudinal bars are correctly held in position with the help of transverse reinforcements. They are also helpful to resist the shear on the column or torsional resistance of the column. So it will help to enhance the shear resistance as well as the torsional resistance in the column due to external loads. Okay, so these are very important things to be kept in mind. And if you refer page number 49, clause 26532, we have a set of important caudal recommendations which will give you insight, which will help you to determine the pitch and the diameter of the transverse reinforcement. So we know that the transverse reinforcements are provided in the form of lateral ties like this, separate elements in the form of loops like this, or they may be provided as continuous spirals or helical reinforcements. Okay, so we have caudal recommendations separately for lateral ties as well as for spirals or helical reinforcements, where it is important that we define the term pitch. So you see, what is pitch? For lateral ties, the pitch is the center to center spacing between lateral ties. Okay, these separate lateral ties, the center to center spacing is what we call as pitch. Or in case of spiral reinforcements or helical reinforcement, it is the center to center distance between two adjacent twists or turns of helical reinforcements. Okay, so two adjacent turns of helical reinforcement, we call it as pitch. Okay, so we have caudal recommendation to determine the maximum pitch. So maximum pitch can be found out if you find these out. Okay, so you can refer to these caudal provisions while you determine pitch of lateral type. You have provision to define a minimum diameter also for lateral ties. The minimum diameter to be provided is 6 mm. You can it should not be less than 6 mm. There may be a correction to the IS code which you have with you. Some are wrongly written as 16 mm, so please correct it. It is 6 mm. The minimum diameter of lateral ties to be provided is 6 mm. It is not 16 mm. Okay, so likewise pitch is defined for helical reinforcement also. The minimum diameter also is defined for helical reinforcement. Okay, now coming to the design of short columns. So here we restrict our studies only to the design of short columns. We are not interested in long column designs. So these are again based on certain assumptions. So the assumptions for limit state of collapse in flexure we have already defined while we studied about the design of singly reinforced beams. There a set of 5 or 6 assumptions we have already learned, and in addition to these assumptions which we already had learned, the code defines another 2 assumptions exclusively for compression members. Okay, so these are also to be given consideration. So the 2 important assumptions are the maximum compressive strain in concrete in axial compression is taken as 0.002, but in case of flexure it was the ultimate compressive strain in concrete was 0.0035. so this is suitably modified into 0.002 for compression members. And there is another assumption, the maximum compressive strain at a highly compressed extreme fiber in concrete subjected to axial compression and bending. Okay, so this involves axial compression and bending, which means that the load is an eccentric loading, and when there is no tension on the section shall be 0.0035 minus 0.75 times the strain at the least compressed extreme fiber. So suitable assumptions are being made for the design of column. So if a question comes for the examination to list the assumptions for compression member designs, then you have to write all the assumptions which you learned for flexural members plus these 2 assumptions also you have to write. So this you will find from page number 70. Now coming to the design of short columns subjected to axial load. Okay, pure axial load. So we have discussed that when we design columns subjected to pure axial compressive loads, you have to determine minimum eccentricity, and we know how to determine the minimum eccentricity. We have already discussed. Page number 42 will give you the minimum eccentricity. So once you find the minimum eccentricity, you take page number 71 close 39.3. there it says that when the minimum eccentricity does not exceed 0.05 times the lateral dimension. So the minimum eccentricity you have found it out earlier, and if it does not exceed 0.05 times the lateral dimension, then axially loaded compression members may be designed using this particular equation. This is very important equation. You have to keep note of it. Page number 71 close 39.3. Using this expression we are going to design a column. Okay, so this equation is very important to determine the design load on short columns with the axial loads. Okay, so PU is equal to 0.4 FCK AC plus 0.67 FY ASC. PU is the axial load on the compression member. FCK is the characteristic compressive strength of concrete. ASC is the area of concrete. Okay, it is the area of concrete. It is not the gross cross-sectional area of the column. It is the area of concrete alone. Okay, keep it in mind. Fy is the yield strength of the reinforcement steel. The main bars used, the longitudinal bar used. Then ASC. ASC is the area of longitudinal reinforcement for the columns, the longitudinal bars, cross-sectional area. Okay. Now this equation is applicable if the lateral ties are used as transverse reinforcements. If in place of lateral ties we are using helical reinforcement, then this equation has to be suitably modified. The modification is very simple. You have to multiply by a factor 1.05 in addition to these terms. So you just have to multiply 1.05 into these terms. Okay, 1.05 into within brackets 0.4 FCK ASC plus 0.67 FY ASC, because by doing this factor, by multiplying by this factor 1.05, we mean that by using helical reinforcement, the lateral ties will in place of lateral ties, compared to lateral ties, the helical reinforcement will contribute better to the strength of columns. Okay, so compared to lateral ties, helical reinforcements are more better because it gives more strength to the column. How much strength? It gives additional 5% strength is given. That is why we have used the factor 1.05. So this is again given in clause 39.4, that if we are using helical reinforcement, then you have to multiply these terms with 1.05. Now, coming to the design of columns with uniaxial eccentric loads. So previous case was for columns subjected to pure axial loads. Here it is for uniaxial eccentric load, the compressive load with eccentricity about one axis. So in this case, the design becomes slightly complicated, but to evade such complications, we make use of SP16 charts. We call them interaction diagrams. Okay, so you just have to refer to SP16 charts listed here for designing short columns subjected to uniaxial eccentric compressive loads. So the charts from 27 to 38 may be referred for rectangular cross-sectional columns with reinforcements distributed equally on two opposite sides. Then charts from 39 to 50 may be used for rectangular columns with reinforcement distributed on all four sides. Okay. For charts 51 to 62 may be referred for columns of circular cross-section. Okay. So we will now study and solve numerical examples related to the design of columns. Thank you.